Hello. This video is going to be a brief introduction to decline curve analysis. And this is where, in an empirical, almost a sort of extending the curve type fashion, we make predictions of future production. And really what we're doing is we're making a base case prediction against which we can look at different things that we might be doing, like drilling more wells or injecting other fluids. Okay? So it's a relatively brief presentation. I'm going to spend too much time on it, but at least I'm going to introduce the idea. And I'm going to introduce the idea of decline and plateaus. So if I bring up the whiteboard, so I can do some drawing. Okay, so let me explain what we're going to do. So let's have a plot here. On this axis is time, and on this axis is production rate. I'm going to call this production rate Q. It's normally measured in, say, stock tank barrels a day. And so 0. Q is technically, okay, it's DMP. MP is the cumulative production. So that's the total amount of oil we've ever produced. Okay, so Q is the production rate, okay, in barrels per day. T is time. Now, funny enough, time is normally measured here in years. Okay, so we, as said, time 0 may be the day, the time that you first discovered oil. Okay, let's imagine that. And we're typically, just so that we get some sort of scale, you know, this may be 10 years, this may be 20 years. Normally, if you're an independent oil company, you want to produce most of the field within 20, 25 years. Okay, so that's your typical time scale that we're looking at. Okay, so what happens? Well, you've discovered oil, but then you need to obviously plan what to do. You need to do some of the analyses described already in this series of videos. So nothing happens, then you start drilling a well. Okay, you may have problems, and then your well comes on stream. So your flow rate goes up, then it sort of plateaus, then you drill a few more wells. And so what you're hoping to is to get to a stage relatively rapidly, which is this. So this is not a terribly good scale. This may be of order 1 year. So within a year or so, depending on obviously the size and complexity of the field, you hope to drill sufficient wells that you're producing at what's called a plateau rate. We'll call this is your plateau. Now, why do you have a plateau rate? Okay, you have a plateau rate. A plateau rate is where you're producing at a fixed flow rate. And you might say, well, surely if the reservoir pressure starts high and goes lower, then maybe the rate declines over time, which is where we're getting. But often what you do is you design your surface facilities so that they will handle a maximum amount of oil. And so you're running your facilities at maximum. You can't actually produce any more oil because you've got no way of dealing with it. So you sort of cut back on the chokes if the production is too great. So you want a plateau period, and that plateau period normally may last out to 10 years, if you're lucky, maybe only 5 years or so. And then what's going to happen is, you know, regardless of what you're doing, you're going to find that your production starts to go down. And when this happens, this is called you're on decline. And this production is declining not because you're sort of, you know, say you're part of OPEC and you're deliberately tightening the valves and restricting production for sort of, I would say, political or financial reasons. No, you're on decline because there's a problem down in the reservoir, right? It's the reservoir itself cannot continue to produce oil at a sufficient rate. And the reason for that is obvious, that and it's twofold related to what we've already said. The reservoir pressure has dropped. So the pressure that's driving the fluids from the subsurface to the surface, to the top, is lower, and so there's less of a driving force. The second reason is that you may be displacing oil, for instance, by water, and you've displaced most of the oil that can move. And so there's not much mobile oil, movable oil left. Okay, so you're on decline. So how are we going to analyze that? Now, what you should do is you should have a proper, rigorous scientific model of what's happening down in your reservoir, and you solve relevant equations to understand this behavior. And that's what we're going to cover in the next big step in this course when we talk about fluid flow. But what I'm going to do here is just do this empirically. Okay? So what we do is we define a decline rate. Okay? And this is an important thing to know, because people will say, okay, my reservoir's on decline. What is my decline rate? B is 1 over Q by T. And clearly there's a minus sign here because Q is declining with T. So this is a negative number. It's the fractional rate and B. And normally what we do is how this is actually measured in terms of units. B may be in stock tank, Q may be in stock tank barrels a day, but you may take the production, for instance, last year and the production the same time this year, and you look at it on a yearly basis. So the typical units of B are actually 1 over years. Right? Okay, so Q, the units of Q cancel. Okay, so we may be looking at a decline rate of, say, 10% a year. So typical decline rates, okay, they can be looked at around the world. Once a field is on decline, typical decline rates are about 5 to 20%, right? So 0.5, 0.2 are typical values. Okay. So that's your decline rate. Obviously, you can look at this equation. It's not terribly difficult. If B is a constant, well, then you can integrate this equation. And let's actually get some constants out. Let's call this time T0 when you first go off plateau, and Q0 being the plateau rate. Then you can write that Q in the decline phase, so in the red phase, not when it's on plateau, it's a constant, not when it's building up, because that's dealt with, am I drilling the wells, okay? But when it's on the decline, so in this red area, Q is Q0, E to the minus B, T minus T0. And really, if you're struggling with that step, you need to be able to read mathematics, okay? So if 1 over Q dq dt is proportional to B, it's exponential, okay? Or if dy dx is proportional to y, it's exponential, okay? You should be able to just see exponential rate. So it's an exponential decline. Okay. Now, do we see exponential decline? We do in some fields, okay? And it's a good first approximation. Now, that then allows you, obviously, more or less by a curve fit, obviously you've got an equation now, you can go into the dotted region, which is your prediction, okay? Now, as predictions go, it's not terribly marvelous, it's just a curve fit, okay? But it gives you very quickly a base case. So you can say, I've got a field with, say, a 15% decline, that's rather rapid. On that basis, you know, just extrapolating, you know, very soon I might get to some minimum flow rate at which the value of the oil that I'm producing is less than the cost of running the facilities. And so I have to abandon. Okay. So you might say, well, look, we got an abandonment period here of about 20 years. But you might have a lease for another 5 years and you say, well, this isn't looking very good. What could we do? So then what you might consider is you might say, okay, what I'm actually going to do is I'm going to try and improve my recovery. What I want to do is I want to do something here, maybe drill more wells, do EOR, okay? So you may want to boost recovery. So this is maybe an EOR process or infill drilling. And the additional recovery you get is clearly the area under this graph. Okay? So the additional recovery that is results from whatever you might impose on the field will be the area under this graph. So this is your base case. So this doesn't look good. You're going to have to abandon the field maybe before the end of the lease. That you don't want to do this. So then you say, okay, I'm going to plan infill drilling. I'm going to plan enhanced oil recovery. This is what I get. So this may be real data, or it may be predicted data based on a proper simulation flow model, a detailed model of what's happening in the reservoir. Okay, and then obviously the difference between those two is essentially the additional recovery. And the question is it worth it? Right, so there's an economic decision to be made. Okay, that looks pretty easy, and there's a reason for that. It's, you know, decline curve analysis, as I said, isn't the world's most complex case. So I'm sort of more or less going to leave it there. You should know what a decline rate is. Okay, 1 over QDT. It's typically measured 1 over years. Its typical value is around 10%. But I'm going to show you just one other example. Okay, so I'm actually going to clear everything here. It just makes it a little bit easier. And I'm going to take one case. So we'll keep with the definition of B is minus 1 over Q to Q to T. And I'm going to look at one example. So when we come to look at shale, this is Q, this is T. And the behavior of shale oil and gas is a little bit different. So, you know, I talked about decline, but I also gave this idea that maybe, you know, there's something else going on. And the answer is yes. With a conventional oil and gas field, most reservoir engineers will produce a geological model of the structure of the reservoir, and then they'll solve for flow numerically, and they'll make more rigorous predictions of what would happen under different scenarios. Okay, and I'll introduce the flow equations, as I said, later. But there's one now booming group of hydrocarbon reserves for which things are both, I won't say simpler and more complex, and that's shale oil and gas. We don't properly understand the behavior of shale oil and gas. It's also done as a sort of almost industrial process. Thousands and thousands upon thousands of wells, horizontal wells, are being drilled in the US. And so the behavior of each well, although it interferes with the others in, again, potentially a complex way, is sort of treated a little bit separately. So with shale oil and gas, people don't have a detailed simulation model. No, they know that there are these huge reserves, potentially of shale. You drill your horizontal well, you fracture the rock, you produce. And what you see here, you know, if this is when you start drilling and this is 0, you see a rapid build up like this, okay? And then you see a decline, okay? And really at this point, predicting the decline, particularly predicting the decline rapidly, is very useful because it says, right, when I drill this well, I'm going to get this much oil and gas. And the time scale here, you know, this may be looking at about 1 year. Okay? So you don't have a plateau rate. You go immediately, once you get to the maximum, very rapidly, within about a year, you're on decline. And so the total life of the field may just be sort of the order of, say, 3 years. Something like this. Okay? So what is the nature of this decline? Okay? So that's actually quite important because throughout the field, you start producing, you see a decline over, you know, maybe a week or two, right? Then you can extrapolate. And of course, at this point, there's nothing much you can do. You're not going to abandon the well, but it may be, am I going to drill other wells in this formation? Am I going to look somewhere else? Okay. And okay, you might say, well, you could just look at this peak production, but it's also trying to extrapolate the whole. Okay. So what happens with shale? So I'll give you an idea, and it's very simple. So what happens is you have your horizontal well and you produce all these fractures largely. So when I look here, what is actually this a picture of? This is actually a horizontal well like this, and the fractures are aligned vertically. So now, rather interestingly, you know, what is sort of the behavior? The behavior now, if I blow up between two fractures like this, okay, you've got two fractures. And at the fractures, because they're conductive, and here's the well, okay, the pressure's very low. The pressure's low in the well, the pressure's low here, but the fractures are where the flow is. There's no real flow into the well here because there are no fractures. So you've got these fractures at low pressure. And then what happens is over time, because there's low pressure here, high pressure here in the middle of the field, right? So you go from high to low pressure, right? The gas and the oil flows into the fracture. And of course, as it does so, the oil and gas are expanding, their pressure is decreasing. So there is essentially a pressure wave that moves through the material. And again, when I introduce fluid flow, we can actually do the equations quite rigorously, but it turns out that it's a diffusive process. So what you find, basically, is that the length over which the pressure is declined goes as the square root of t, square root of time. And that also is proportional to the cumulative recovery, MP. And the reason for that is this zone, basically here, is a low pressure zone. Okay? So you have a low pressure zone that essentially diffuses out into the material. So that's what we're looking at when we look at fractured reservoirs. And so MP, the cumulative production, roughly speaking, scales as T to the half. Okay, well that It's interesting. What can we do with this? Well, let's now go through the equations. What I'm going to do is I'm going to have to clear this, and then I'm going to show a bigger diagram of that to make it a little bit clearer. Okay, so let's just do a bit of the maths, and then I'm going to show the schematic later. Okay, so MP is t to the half. So Q, right? There will be a couple of derivatives here. Is dMPT, right? And that scales as t to the minus a half, right? Because I go half t to the minus a half, but it scales as, right? This is just we don't know the proportionality. The proportionality is actually set by, how high it goes. Okay, so then dq dt, right? That goes as minus a half t to the minus 3 over 2. So B scales as 1 over q, so that's t to the minus a half, q divided t, and that's 1 over q, so it's plus. The minus signs disappear, so that goes as 1 over t, which goes as q squared. Okay, so with shale oil and gas, what you tend to see is that Q here, Q goes as t to the minus a half, so 1 over root t. So it's not exponential at all. It's not an exponential decline, but a root t decline, okay? Sometimes what is written as B is written in terms of Q, so B goes actually as Q squared, okay? And sometimes what this is called is hyperbolic decline. And funnily enough, the exponent is sort of defined the other way, and that's just traditional. So B goes as Q to the 1 over A, so A is a half, and this is a type of hyperbolic decline. But basically, it's a 1 over root T behavior. And you see this for any diffusive type process. So you see this for shale oil and gas, where you see a pressure wave moving out. You see it actually in so-called well test analysis, when we're looking at how the pressure behaves. You're actually going to see it at the end of this course in imbibition processes, again, where water soaks in to a porous medium. And again, that's a diffusive type process. So any diffusive type process goes as root T. Any advective process goes linearly with time. But I'm not just pushing oil and gas out. Actually, I'm using pressure to do it. So it's a diffusive process. Okay, so that's great. The problem with that is if you integrate, NP goes as t to the half. So at infinite time, you produce an infinite amount of gas, which seems that's like a bit weird, because I said, well, how much gas do you produce? And it's very much a finite amount. So how do I reconcile that? So let me get rid of this. We'll create some space, and then I'll explain. Right, and that's why I said I do a blow up these fractures. So let's actually choose another color. Right, maybe it makes it a bit different. So here are these fractures, these vertical fractures, okay? And they have a spacing L, okay? So what happens is, as I said, you drop the pressure, and there's some pressure, low pressure wave that moves out. The fluids, if we do this, the fluid is actually moving towards the well in this direction, okay? And this is true, everywhere. So while the pressure is sort of moving out, we're going as Q is t to the minus a half, so that's fine, okay? But then what happens? What happens when the two pressure waves meet each other, right? Okay, and that's when T, so if L over 2, right, goes as T, and that's going to be, I'm going to call it A to the half. Okay, so once the pressure wave has moved L over 2, and L is the spacing between the fractures, okay, so you should have some estimate of that. So you have this diffusive process, and the diffusion coefficient is related to the properties of the rock, the underlying permeability and compressibility, in fact. Okay, so you have this diffusive process, but once you've gone half the spacing, because you're coming from both sides, okay, so you have some abandonment time, TA, which scales as L squared over 4, but there's a diffusion coefficient here as well, okay? So if we go that the distance that you move, your x goes as root dt, okay, when x is L over 2, okay, then you get L squared over 4 is equal to dt, and T is A, then dTA is L squared over 4 times the diffusion coefficient. Okay, so at that point, right, the scales of the spacing squared, then you go down into an exponential decay, right? So once you reach TA, you then have an exponential decay, and I think you can, you may not see why exactly it's exponential, but the low pressure waves have met each other. There's then some sort of slow equilibrium to sort of the low pressure that's related to what you see in the fracture, but the flow rate then declines exponentially. And of course, at that point, you have a finite recovery. So that's how you analyze shale oil and gas. You find your initial peak, and then obviously, you know, how big that is, you know, tells you it's good or bad news. You then tend to follow this root T decline. Then you get to some sort of almost abandonment time here. And beyond there, there's very little recovery. There's just a sort of exponential tail, but that's what gives you a finite recovery. And so MP, roughly speaking, is proportional to the abandonment time to the power of a half. Okay, so as you can see that's proportional to L squared, so it's related to L. And that again makes sense, right? The larger the spacing, the more you recover from each fracture. Okay, so I'm going to finish here. It's a very simple-minded, actually, analysis of shale oil and gas. I'm not by any stretch of the imagination pretending that's complete. There are lots and lots of other complexities. It turns out that this diffusion coefficient is highly non-linear. Obviously, you can't have an infinite fracture spacing because then it takes forever for you to recover your oil or gas. Okay, and there are many, many more other complexities. There's also interference with other wells. But generally speaking, where decline curve analysis is used most frequently now in the oil industry is in the analysis of shale oil and gas. And we tend to find this initial root T decline, this so-called hyperbolic decline, followed by an exponential tail. Okay, so I will stop there. As I said, you know, a somewhat empirical approach to this problem. What I'm going to do in the subsequent lectures is we'll introduce fluid flow, and we'll deal with this a bit more rigorously with partial differential equations to give you an understanding of why we have the behavior that we see. Okay, well, thank you very much.